I'm going to discuss the photoelectric effect. Literally, photo means light, electric means electricity. Photoelectric, creating electricity with light. So we're going to investigate the effect of changing the light on these electrons, see what happens. We're going to explain what's going on. We'll be able to do some calculations and figure out the formulas that are required for this. But before we do that, we know that light actually is a wave. We have done Young's double slit experiment, and that has two slits. For example, light shines through it, interferes with itself, and creates bright and dark spots. So light has been proven to be a wave. If light is a wave, in the photoelectric effect, you can shine light onto electrons and they will absorb the energy and then get ejected. If all light should work, to be honest, because if it has low energy, it might take longer to absorb and then finally come out. So it takes some time for the energy to reach the level it needs to be, and then it can come out. Light with less energy takes longer. Light with high energy will end up obviously being faster. Brighter light should release faster electrons, because if there's brighter light, it means it's more energy, right? Higher intensity should also create electrons that need higher potential to stop them. These are all things that we should know about. More energy light, more frequency should release more and faster electrons. All that's wrong. That says to us, well, light, how can it be a wave? This is when Einstein came along and says, well, perhaps light can act like a particle. And this is where photons and packets and stuff come in. So here is an example. We have this little lamp. Its brightness is off. It's shining infrared light, which has a high wavelength, and let's shine some light onto it. Nothing. Let's increase it. Nothing. Let's make it even more bright, full brightness. Nothing. Even after a long time. Nothing. Okay, let's decrease the wavelength. Now I'm bringing it into the visible spectrum. This is visible light over here. Nothing. We'll bring it starting from maybe here. Let's bring it closer. Change the wavelength. Now by changing the wavelength, I'm changing the energy. Still nothing. Let's keep going, and keep going somewhere along here. Will there be a sweet spot? Yes, look at that. We now have electrons moving across. I have now reached the minimum energy needed for electrons to leave. So I'm shining light onto this plate. This wavelength here carries the energy needed to make an electron leave. Fine. Now, what happens if I increase the brightness now? Let's check what happens. Well, it looks like the speed is the same as before, but I have more electrons coming out. Let's make it even brighter. Let's confirm. Let's make it even more bright. Same speed, but now even more electrons are coming out. So that's an important part. The brightness or the intensity only affects the number of electrons coming out. This is not very bright, so very few electrons are coming out. Look, they have the same speed, same energy. So the brightness affects how many electrons come out. The way to help you understand that is through here. If I am shining light onto something, each piece of light that comes out like that, we call them photons. If I increase the brightness, look what happens. I will have more photons coming out. Each photon interacts with one electron only. That electron will absorb the energy of the photon and immediately come out, just like this. Any extra energy left over will become kinetic energy. That's why they can move. So, back to this one, because it's nice and simple. I increase this. Let's see what happens now. I am now using purple light. Look at that, they're faster. This was the ones that were released earlier, and now these are the new ones I've just released. Increasing the intensity will just mean more electrons will come out. Now if I decrease my wavelength, that must mean I'm increasing my energy, because look, I am having faster electrons come out every time. And you can go on and on and on into UV light and stuff, and you will notice that more and more energetic electrons. Fine, let's bring it back to here. Yeah, that's fine. Next, this is fine. I now have electrons moving. This is a current. Electrons are moving. I have created electricity using light. I can also stop the electrons coming out. I want to see how much kinetic energy the electrons have. Well, that's fine. I can just use my battery and I can try to increase the voltage to try and bring the electrons back. The lower energy electrons are coming back, and because I've set it to 1, actually everything is coming back. So I can see the voltage that I need to stop the electrons from leaving. We call that stopping potential. And we'll talk a little bit about that in a bit more detail. So this is the general idea. Let's come up with some of the formulas that we need to use. Let me use good old red pen and reduce this. Okay, so the energy that we have in an electron, energy given is E equals hf. This is the general formula. H, this is Planck's constant, and is given to you in your exam. Planck's constant is 6.63 times 10 to the minus 34, and frequency is of course just frequency, measured in hertz. If you are savvy and you remember, frequency is the speed of light divided by wavelength. This is the wave equation. This is the wave equation. Instead of writing frequency, I can substitute h, not f, but c over lambda. I can write c over lambda. This will work as well. For some reason, my mouse is not pointing in the right place. Now, what does this mean? Energy is equal to hf. It's directly proportional to my frequency. However, look at this. It is dividing by wavelength. It is inversely proportional to my wavelength. So that makes sense based on what we have done over here in our simulation. This is my wavelength. I am reducing my wavelength and I'm getting more energetic electrons. Fine. But you noticed over here, no matter how bright it was, nothing happened. Electrons weren't being ejected at all. There were no electrons moving around. So that means I need a minimum energy required. And we have a term for that. It's this little phi symbol right here. This is the work function, the minimum energy needed to release an electron. And of course that will be h, the threshold frequency, f naught. This is the minimum frequency needed, or I could say h c over threshold wavelength. This one here. This is the exact wavelength that you will need, which was around here somewhere. This is the exact wavelength. You can actually go ahead and calculate it, but we're not going to do that right now. We're getting the idea. So this is what we call a work function. Work function. And this tells me the minimum energy I need to eject an electron. Min energy. Sorry, I'm just using my mouse here. I am going to upgrade to a pen in my next videos, so keep an eye out for that. So this is just on the mouse, so it's not really very neat. Okay, great. So now we have equals hf. We have this. Next, we did also say if I have more energy, the extra energy left over after it gets ejected becomes kinetic energy. See the speed? They're moving faster. So that means we can also have some sort of kinetic energy involved too. So in total, in general, a photon comes in with a set amount of energy. Some of that energy will be used to release an electron. The remainder of that energy will become kinetic. Brightness, again, just to reiterate, the brightness just means more photons, which means more electrons. That's all. Same energy. Look, speed's the same. I can decrease my wavelength, which should increase my energy, thus making them faster. Let's find out. And yes, they are much faster. So that is the photon's energy. I can write that out as well. The energy of my photon, whatever that is coming in, must be whatever energy I need to leave, and whatever left over becomes kinetic energy, Ke. So this is a general equation that links them all together. You can calculate the kinetic energy if you know the energy of the photon and you know the work function. The remainder will be the kinetic energy. In another video, I will do some more practice questions on this. Another thing we should know is about this stopping potential. This stopping potential is trying to cancel out this kinetic energy. So it should be equal to the kinetic energy. Well, that's voltage. You know from previous terms, W equals QV. This is a formula for work done. And this is voltage, this is the charge. Well, of course, in this case, our energy is going to be our kinetic energy. This is the energy that I'm trying to match. I'm trying to catch these electrons that are coming out, with whatever speed that they have. That's my kinetic energy. Well, Q, I've already said multiple times, I've used this word electron, so let's call it E. This Q becomes an E, and that is still going to be V. This is my stopping potential. This just happens to be equal to the kinetic energy. Now that leads us on to the types of energy, or the units of energy. We have joules, and we also have EV, which is 1 electron through 1 volt. This is EV. And we have done this in the previous term. You want to convert to and from EV, you have to use the charge of the electron, which is 1.6 times 10 to the minus 19. And that is electron volts. Makes it easier. Some numbers will be smaller. Rather than having to deal with like 3 times 10 to the power of minus 19, you can just have 2 EV, 3 EV, something like this. And I will discuss that in our next video. I think this is getting a bit too long. Okay, thank you.